Solving polynomial equations by factoring. Okay, so obviously we're going to be using the skill of factoring in this lesson, so if that's something that you still need a little bit of review on or you're having trouble with, you need to check section 5.4 in the Algebra 2 book or find the videos in the chapter 5 section on factoring. You will notice in the notes here we have a little bit of a review, factor by difference of cubes and sum of cubes. And before we do those two though, we're going to start with factoring out a greatest common factor. Can you divide out a common factor? That is always step one. That is always the first thing that you start with. Try to see if you can make your problem a little less cumbersome, a lot of smaller numbers, things like that. So you want to try to break it down if you can. The difference of two perfect squares, some key factors here are that both the first term and the last term both have to be perfect squares. And I know some students are still really struggling with perfect squares. You certainly could create a list of perfect squares to have in your notebook. Example, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16. These are your perfect squares. And you could do those all the way up to 12 if you wanted to, and then you would have them. Don't forget that that also goes with variables x times x, x squared, or x squared times x squared would be x to the 4th, right? And then x to the 3rd times x to the 3rd gives me x to the 9th. So these are all perfect squares when you're dealing with variables, okay? Because remember, you add the exponents when you're multiplying variables. So if you're adding these exponents, you're looking for exponents that are exactly the same, that are going to give you that combined exponent with for your end product. So 2 plus 2 would give me the 4. 3 plus 3 would give me the 9. So these are perfect squares. Awesome to have in a notebook. If I were you, I would certainly take some time to copy those down, maybe even on a 3x5 note card, and 3-hole punch it and stick it right in your binder. You'd have a list of your perfect squares to refer to if you're having trouble. So back to our difference of two squares. The first term and the last term both have to be perfect squares. And then it's the difference. So it needs to be a subtraction problem. If it's not a subtraction problem, move on. It's not the difference of two perfect squares, okay? And then those break up such that your two parentheses are sort of the square root of your A term, the square root of your B term, and one is positive and one is negative. And then we have an example to look at. 9, what times itself gives me 9? That's 3 and 3. What times itself gives me x squared? That's x and x. So my first term is 3x. If I took 3x and multiplied it by 3x, ooh, sorry, my marker keeps sticking. Let's try that again. If I multiply 3x times another 3x, I then get a 9, 3 times 3, and x times x, x squared. So I'm on the right track. Then when I look at my last term, the 64, what times itself gives me 64? 8 times 8 again. If I take 8 and multiply by 8, I do get 64. You will notice, though, that if I were going to multiply this out, I did the first and I did the last. I did not do the outer and the inner, and the reason for that is they cancel. That's why one of them has to be positive and one of them has to be negative. So 24x positive, 24x negative cancels each other out, and we have no middle term. And because the negative 8 times the positive 8 was negative, that's a negative in the middle. So we're undoing the FOILing process when one of the terms is positive and one is negative, and they're exactly the same binomial. Difference of two cubes and sum of two cubes we also did back when we were doing factoring. It's really important that you just pay attention to the fact that it's just a pattern, essentially. You're going to cube root the items. So you're going to cube root the A, and then you're going to cube root the B, and then what you get for your answer is your A and your B. And then you just plop it into this formula, which is a pattern, okay? And so when you look at the example, we have x to the 3rd minus 27. So in other words, what times itself again? What did we cube to get x cubed? The answer is x. So that becomes the a in your formula. And you'll see that we put it here for a, and we squared a here. Excuse me. You're going to cube root your 27, so what times itself again gives you 27. 3 times 3 is 9, times 3 again is 27. So your b term is going to be 3, and you'll notice we put it in here, and then we just took the sign from the formula, and then we did the b times the a, or a times b here, right? So 3 times x gave me 3x, and then this was supposed to be b squared, so I did 3 squared and got 9. So you're breaking down, cube rooting the first term, cube rooting the second term, and then just using those answers, the x and the 3, and putting them in the formula. Same thing with sum of 2 cubes, it's just that the signs are different. The first one was a difference, the second one is a sum, and also pay attention to the signs here. They are the opposite of what you're starting with. So if you have a subtraction here, it's an addition here, and if it's an addition here, it's a subtraction here. Okay, the last term is always plus b squared. So those terms, signs for the first two things are opposite each other. Just be careful about that. So how do we solve a polynomial equation by factoring? First of all, we figure out which of our situations do we have. Which of all of these choices do we have? Second, you actually factor it out. And third, you use the zero product property or the quadratic equation to solve. And that means then you're going to find your zeros. Once you've factored it down, you set those factors equal to 0, and you try to figure out what your roots are. So let's clear this, scroll it up, and we'll actually practice a few together. So we have these 3 examples where we're going to need to figure out what is it that we have here, which of the situations, and then what do we do about it. So when I look at this particular thing, number 1, the first thing that I'm clued into is that it's a cube. It's x cubed. And so I have to make sure that 8 is also a perfect cube. So if I cube root x to the 3rd, okay, anytime you have a perfect cube under a cube root, they're inverses of each other and cancel, leaves me with x. So that's going to be my a. And then I have to cube root the 8. So if I don't know whether 8 is a cube root, again, I can have cubes on the side of my paper, or maybe on the back of that 3x5 card I suggested. 2 times 2 times 2 is 8. So that means that that is 2 cubed, and that equals 8. Okay, 2 cubed is 8. So again, another strategy for that, if you don't know or you're not sure, is to take your 8, break it down, and see if when you prime factor it, do you get a perfect cube under your cube root? And the answer is yes, you do. You get 2 to the 3rd under a 3rd root. They will cancel. Your answer is 2. The cube root of 8 is 2. That's going to be my b term. And since it's the difference of 2 perfect cubes, then I'm going to use my formula. I'm going to just go up and snatch my formula right from the top of my page, and then I'm going to plug in my terms. So a minus b, x minus 2, and then I have x squared, a times b, so plus 2 times x, plus b squared, 2 times 2 is 4. Put that in as 4 and not 2 squared, okay? Make sure you do simplify that. So now what I have here is this situation. I have an equation that I now need to try to figure out, solve, see if I can figure out what the roots are. So here's how I would do this. First of all, if it's a binomial, it's very simple to just set it equal to 0. Add the 2, and I know for a fact that one of the roots of this particular polynomial is 2. So I found a root. Now I have to find the root of this second factor, which is a trinomial. I have many different choices here. I can try to factor it if I want to. So I might look at the 4 and see, do any of those factors of 4 add to the 2x in the middle? And there is no way for me, using 1 and 4 or 2 and 2, to obtain that positive 2 in the middle. So this is not factorable by our good old-fashioned factoring strategy. So what's left when you can't factor it? the quadratic formula. So we're going to use the quadratic formula for this one. We're going to do opposite of b plus or minus, square root of b squared, that's a squared, minus 4 times a times c all over 2a. That's our quadratic formula, okay? Really need to commit that to memory. Make sure that you know what it is. So we're actually going to plug that in, okay? I'm going to move over here where I have a little more space. I'll erase it after when we get ready to do number 2. You might be able to just finish at the bottom of your page. I'm running out of space here. So we have the opposite of b, so negative 2, plus or minus the square root of b squared, that's 2 squared, minus 4 times a, which is 1, times c, which is 4. And the whole thing is over 2 times a, which is 1. All right, let's evaluate the discriminant. So 2 squared, 2 times 2. So negative 2 plus or minus the square root of 4. And then I always ask my students, you know, do this part first, drop the answer down, and then I ask them to multiply all of this part out, including the negative, and drop the answer. So we're going to do negative 4 times 1 is negative 4, and negative 4 times positive 4 is negative 16, okay? And then all over 2. And now I can do 4 subtract 16, which gives me the square root of negative 12. If my discriminant, the negative 12, is less than 0, I'm going to have an I in my answer. I'm going to have some imaginary numbers in my answer. So let's break down that negative 12, right? That's negative 1 times the 12, which I'm going to break down 2 times 6 and 2 times 3. And I'm looking for perfect groups of 2, perfect squares. If I were looking for a fourth root, I'd be looking for groups of 4. So I have a negative 1, then I have my group of 2, my 2 squared, and then that little lonesome 3 left over. That 3 is going to stay under the radical. I like to circle the ones that are staying underneath the radical. Square root of negative 1 is I. The perfect square under square root cancel, leaves me with a 2. And then the root of 3 has to stay there. So if I rearrange this so it's in proper order, it's going to be 2i square roots of 3. So now I'm going to go plug that into my equation. Negative 2 plus or minus 2i square roots of 3 over 2. And again, remember the story of the queen in the castle. My queen is here in the castle. We cannot reduce the queen. She's protected by her castle, but we can reduce the number of soldiers outside the castle. So 2 goes into 2 once, 2 goes into 2 once, 2 goes into 2 once. So now I'm really ending up with negative 1 plus or minus I square roots of 3. I don't need to write it as a fraction because it's over 1, and I also don't need to put the 1 in front of the I. You certainly can if you want to. So those are your 3 roots. We're going to have 2 and then negative 1 plus or minus the I square roots of 3. Remember that those are 2 roots, negative 1 plus I square roots of 3 and negative 1 minus I square roots of 3. 2 separate roots there. So there's a total of 3 roots. I would also note that there's a total of 3 roots, and again, my hint was that it was a cubic. Okay, so that kind of tips us off that perhaps we will have 3 different roots. All right? Okay, so I'm going to clear this, and then we'll try number 2. Let me also see if I can scroll the page up a little bit so it's not quite as crowded. Oh, there we go. I'll have more room this time. All right, so let's talk about this one. Again, let's check to see. This is tipping me off that it's a cubic, and then I'm going to have the difference or the sum of 2 perfect cubes. It's subtraction, so it should be the difference of 2 perfect cubes. A lot of times students will say 1 is not a perfect cube. 1 is a perfect everything. 1 times 1 is 1, so it's a perfect square. 1 times 1 times 1 is 1, so it's a perfect cube. It's a perfect everything. So 1 is definitely a perfect cube. 2 times 2 times 2 gives me 8, so it's a perfect cube. And then also x cubed, x times x times x. So those all 3 check out to be perfect cubes. Okay, So I'm going to go ahead and get my perfect cube formula. So a minus b, and then I'm going to have a squared plus ab plus b squared. Okay? And then let's figure out, if I cube root ax to the third, 8x to the third, I'm going to get, for a, I'm going to get 2x. 2 times 2 times 2 is 8. X times x times x is x cubed. And again, we said that the cube root of 1 was 1. So there are my two values, 2x minus 1. Now I have to square a, so that means, don't forget, it means 2x times 2x. And that gives me a 4x squared, so that goes here. 4x squared plus, then I have 2x times 1, so 2x plus 1 squared, or 1. Again, we're solving, so I want you to say 2x minus 1 equals 0. Put that equal to 0 and solve. Add the 1 to both sides. 2x equals 1, and then I have to divide by 2 to get x by itself. So x equals 1/2. So I have one of my roots. Fantastic. And I'm going to get the other root by using, again, the quadratic formula. So the opposite of b, so negative 2, plus or minus the square root of b squared, 2 squared, minus 4, times a, which is 4, times c, which is 1, all over 2 times a, which is 4. All right, let's evaluate. Again, I ask my students to do the square and drop it, and then I ask my students to do negative 4 times 1 and drop it, and then move on from there. So it's going to say negative 2 plus or minus the square root of 2 squared is 4. Negative 4 times 4 is negative 16. Negative 16 times 1 is negative 16. All over 2 times 4, which is 8. Okay? So now I need to do 4 minus 16, so negative 2 plus or minus the square root of negative 12 over 8. Lucky for us, we just did the square root of negative 12, and we found it to be 2i square roots of 3. So let's reuse the information we just used in the last problem, 2i square roots of 3. So negative 2 plus or minus 2i square roots of 3. We just did that in the last problem. Remember, we had the negative 1 times the 12, and then we broke it down, right? And we had that group of 2, and we had this 3 left over. That was our I. So we have I, the 2 came out, and the square root of 3. So remember, we just did that in the last problem. So we don't need to write that all out again. If we have it as a resource, let's use it. Again, my queen is protected in her castle, so we are not going to reduce the 3. We can't anyway by the same number, but we could certainly reduce the number of soldiers. 2 goes into 2 once, 2 goes into 2 once, 2 goes into 8 4 times. So I have negative 1 plus or minus I square roots of 3 over 4. Those are my other 2 roots. So combination of roots. I have 1/2, and I have negative 1 plus or minus I square roots of 3 over 4. There are my 3 roots for my cubic. Okay, one more. Number 3, again, let me clear the board so I have room. Again, let's break it down, see if it's a perfect cube. So I have 27, right? So what times itself again gives me 27. 3 times 3 is 9, times 3 is 27, so 3, and then x cubed is going to be x times x times x. Again, b is going to be 1. So I'm going to go ahead and get my a plus b, and then my a squared plus a, that's minus ab. So minus a times b plus b squared. Okay, so a plus b, 3x plus 1, and then a squared, so that's 3x times 3x. 3 times 3 is 9, x times x, x squared. It's always handy to write things out on the side of your page like that, just to be sure you're doing it right. A times b, so 3x times 1, that's 3x, and then b squared, 1 times 1 is 1. Again, we're solving, so we need to set that binomial equal to 0 and solve. 3x equals -1, and then divide both sides by 3. X equals -1/3. That's one root, and I'm going to use my quadratic formula over here for this root. So opposite of b, +3, plus or minus the square root of b squared, so -3 squared minus 4 times a times c all over 2 times a. All right, so again, square the -3 first and drop it, and then do -4 times 9 times 1 and drop it. So 3 plus or minus the square root of -3 times -3 is +9. -4 times 9 is -36, and -36 times 1 is -36. And we're going to put that all over 2 times 9, or 18. 3 plus or minus 9 minus 36 is -27 over 18. So we got to break down that -27. So -1 times 27, right? And so that's going to be 9 times 3, and 9 is going to break down to 3 times 3. Now remember, I'm looking for groups of 2 because it's a perfect square. So I'm going to have 1 3 left over. So when you go to break that down, you have -1 3 squared, and then that 3 left over. So -1 comes out as an I, 3 squared comes out as a 3, and then we have a 3 left over. So that is going to replace the square root of -27. 3 plus or minus 3i square roots of 3 all over 18. And let's reduce. Again, do not reduce the queen. She is protected in her castle. 3 goes into 3 once, 3 goes into 3 once, 3 goes into 18 6 times. So I have 1 plus or minus I square roots of 3 over 6. So my roots, -1/3, and 1 plus or minus I square roots of 3 over 6. There are your roots. Okay, so that is breaking down perfect cubes, sums or differences of two perfect cubes. Again, difference of two squares I think most of you are comfortable with, and greatest common factor I also think you're comfortable with. The next video will be about factoring using the quadratic pattern.